maybe air conditioned.
Yes. Also, I will pass around this list because I think we noticed that we didn't have enough sheet. Maybe some of you did. So we're going to pass around this sheet of paper. You can put your names. The next time, more food for you guys. Okay. So put your name and email, etc., and then we'll be in touch. Yes. So for the afternoon talk, we have a talk by Professor Sheng from the group of STEM. And he's going to talk about how much baryon asymmetry, and dark matter can be generated by remote black. So it's going to be a blackboard talk.
Yeah, this shows up
Or a whiteboard talk. And great. So lots of discussions.
Okay.
Thank you, Shane.
Yeah, I'm not sure how well is it here because I have a bit of glue, so I try to use mask in order not to back everyone else. So basically, this talk, the idea is we'd like to investigate how much what is the parameter space that black holes can explain bioluminescence. I will explain throughout the talk with that. And then also dark matter. So the main idea, so this ongoing work with study is Ashka with from engaged then from the future. So the main idea, okay, maybe is we have some motion black holes. And since black holes has a like Hawking radiation, all possible particles that exist in the universe. For example, you evaluate and meet a particle or X. So these are called the parent particle, which is responsible for bioluminescence. So this particle is in general not stable, so it can decay and so on. But eventually, they are responsible to generate baryons. Universe. And then if there is a dark matter which is stable, so from the same bunch of primordial black holes, they will start is the basic idea. Then we like to see whether there's a overlap between them. We can explain what are the parameter space dark matter with what mass that space. Okay, what kind of black hole means what mass the black hole? Okay, here I use BH0 to mean the initial mass of the black hole. Eventually will evaporate. So this is the initial mass of the black hole. And then the other parameter which is important is how much you have the black holes. So usually we parameterize as beta, which is defined as the energy density of the black holes. Energy density of radiation at the formation of black hole. So there's a constraint on both of these. So the outline of the plot. So first I will talk about the divided into three parts. properties of primordial black holes. So here I will talk about more like a review the properties and how they evolve, how the speed, how the speed evolve. And then after that, I will talk about this is for one, just focus on one primordial black holes. And then after that, we will look at the constraints on the bunch of the bunch of the black holes. And then the final part, I will talk about how with the space. Okay, by primordial black holes, we start then meaning that they are not formed from collapse of stars, merger of neutron stars, so on. So they are formed in the early universe. So okay, you go along, then naturally I will mention what are the range of masses that we focus on. So the first thing is about if you have a primordial black holes. So Hawking showed that they evaporate the production of rate of particle with the number of particles per time. So energy of particle then given by the down thermal. Now, of course, similar to thermal. Here you have energy of the particle. Then you have the below momentum. So the black hole speed. And there's some sort of temperature of the black hole that is associated with place. And here you have okay, depends on whether you are producing permit for boson will be basically part one. So for permit, it's a speed. This one. And then you have adsorption cross section. The adsorption cross section, which also depends on the speed, and then the orbital angular momentum of the particle emitted and the end. For projection, so okay, the degree of freedom of the particle. So this beta M is also the projection angular momentum axis of spin black hole. And so this absorption cross section is proportional absorption, meaning the incident probability of the Schrodinger equation, the wave of the particle, incident of the black hole minus the reflected power.
Sorry. So, and here you're assuming that the black holes are formed, they form with a speed.
Yeah, it could have speed or maybe
Because I
not.
had the idea that people claim that black holes, since they are formed like spherical symmetric, they don't have a speed.
Yeah, usually it's more difficult to get speed.
Okay.
Yeah, for the formation depends on the mechanism, but you're right. In general, it's spatial symmetric, so not speed.
So it's not a requirement that they have a speed.
No, it's not a requirement. Just that I consider what if there is speed. But here I do not consider the charge of the black hole.
Okay.
Because it has been shown only for black hole for masses like 10 to the 5 solar mass or above, then the charge will be important. But after that, if otherwise they will lose the charge very fast. Okay. So they don't have the charge, but then in general they have speed. It also shows diagram about how they spin down or spin down.
So where does this equation come from?
Sorry?
Where does this equation come from?
This is derived by Hawking. This is the Hawking result, like 50 years or so.
Like, how, like, where does it come from? Like, how did it begin? Like, what does the equation really mean?
This is the equation means the black hole through Hawking radiation. So that's the rate of production of particle number per time per energy of the particle. That is the spectrum.
Okay.
Does it depends on the model of gravity? Because for inflation, for example, we have the Star-based model with so much like gravity model. So would you change this? I don't think so. Well, I think it depends on okay, you mean the gravity? Yeah, because I suppose actually it's Martian or like air or like to compute the production of the particles in the curve of space time. I think for curve, I believe that, yeah, for curve meaning that it has non-zero speed for such shield to speed zero. Yes, but those are just solutions for the right? Yeah. So for example, for Starobinsky, those are not solutions. And the Starobinsky term is referred to during the inflection, where the primordial black holes will form. So why can I use this? Yeah, honestly, I'm not sure whether, yeah, if it's not Einstein gravity, yes, the formula will change.
I guess the formula will change even within Einstein gravity. This is a calculation for curved black holes. For a specific solution within Einstein gravity.
I think this holds either for curve or such huge black hole.
Sorry?
This formula holds for both curve.
Yeah, current Schwarzschild, so for the whole Kerr-Neumann family.
Yeah.
But it is for a specific family of solutions within Einstein gravity.
Okay.
If you change the theory of gravity, it will hold if the solution is the same.
Okay, so you said other kind of black hole solutions, not Schwarzschild, not so then you won't have this.
Yeah, it holds for black hole solutions that are asymptotically flat. So if you bring in, if you grab a black hole within the Sitter spacetime, for example, or Schwarzschild the Sitter black hole, I wouldn't expect the behavior to be the same because the calculation, the basics for the calculation will be completely different.
So for something like Starobinsky, probably this formula does it hold?
I don't know. If within Starobinsky gravity, you can pick a Schwarzschild black hole, so you can choose the Schwarzschild metric somehow, then for that specific metric, I expect this formula to hold. But I don't know whether this can happen in Starobinsky gravity. I'm not familiar with it.
But I think there is a difference. Like when you refer to Starobinsky inflation, I believe that primordial black holes are generated after it. So inflation ends, and then you have to black holes at large scales or small scales. So it's not like these black holes live in the inflationary universe they do after this.
Yeah, but the service correction doesn't drop out, right? This is just there, but it becomes less relevant with time. Yes. But just after inflation, I suppose that is still quite relevant. Or could be.
Yeah, could be. But the thing is, no.
Yeah.
I don't know when you are going to form the black hole. So I think that's the difference. It depends when you form the primordial black holes.
Yeah, okay. Because Stravinsky, I think, give the R square, then how they change the cosmology. Yeah, I'm not quite sure. Yeah. Because this, okay.
This calculation actually holds for late time black holes. So you actually wait for the black hole to settle, and you are working in asymptotically flat spacetime, which means you are ignoring everything else besides the black hole. So I don't really think inflation would matter in this case, because you are making a calculation focusing only on the black hole. So you're treating the black hole as an isolated body to the best extent that they can do that So I wouldn't guess that inflation would play a relevant role in here. But by this, I mean that, for example, when dealing with black holes nowadays, in the present epoch, we don't really consider the cosmological constant, for example.
Yeah, I think that the point with inflation is just that it's likely that
gravity is not GR during inflation.
Mhm.
It's my point, not because the inflation, but because the gravity is not GR.
Yeah, so I guess for an isolated body, you would probably get the something similar. Yeah, the equations of motion could be different. Maybe the O'Hare theorem doesn't apply.
Yeah.
So it could be.
So there's a length field associated or gravitational radius. Shared with the black hole mass. Okay, very low. So for such shield black hole, radius is just twice. Gravitational radius and the temperature of the black hole is inversely proportional to this mass. They get hotter as they avoid it. And okay, since there's a spin, there's a factor which I never remember. Um, for spin, there is a factor which is actually close to one. Then the spin goes to the they always define what is the A star. So A star on the first. So A star is related to the angular momentum, but we define a dimensionless termination. Angular momentum. So basically, if we define it this way, the A star will range from 0 to 1, 0 the speed maximum 1. So just to give you an idea of the temperature of the black hole with respect to the mass. Where is like 1 dB temperature. Corresponds to the 10 to the 10 grams per gallons. So this is black hole is much lighter than solar. The solar is about 10 to the 30. Once or 10 to the 33. That's not okay. But something much bigger. So okay, this like the spin, if they lose the spin, so basically they go back to the slot shield. So you can see if you have a black hole of 10 to the 10, then essentially you can emit all the standard model particles. Because they have enough energy. So this is 1 keV. So that means the black hole of 10 to the 10 grams or lighter, it emits all the standard profile share.
This is a thermal spectrum.
Yeah, the thermal spectrum.
So would you expect to emit more massless particles, low energy particles than high energy? No, maybe you're emitting more particles that are around temperature.
Yeah, around the temperature. But eventually, I don't remember. Yeah, they emit eventually. Yeah, everything that there's a ratio. But I think it's more or less proportional to the degree of freedom. For example, you have most fermions, so almost all the energy goes to fermions. Down to the global. Okay, like this global.
But if particle has zero energy, for instance, there's no emission because there's an omega squared.
This is actually the energy of the particle. So when you want to calculate the total number, you can take all the energy. Right? So from the mass of the particles, yes. So you're saying the emitted particle, whether the energy is very high. So the energy will be now similar to the black hole temperature. That's a generate expectation. Whatever temperature is, the particle will be relativistic. Whatever everything which is emitted. Or this 10 grams, exact or
And then this cross section is because you have some background that's impinging upon the black hole and then can absorb or reflect. What is it? I don't know this cross section.
This is basically it's called a grain body factor. It's not exactly perfect. I think later I will show a plot. So basically, they solve this using like Schrodinger equation in the potential. Is the background of black holes. The wave for the particles like spin 0, spin half, spin 1, and then they will have a different absorption probability. So everything that's incident will not be there will be some reflection. They have some
Just a physical picture to understand. So what is being scattered?
it's the particles the
So the background that's being scattered of the black hole or particles that are emitted from the black?
yeah from the yes the particle emitted from the black holes and
So they just go outwards.
yeah go outwards and yeah I don't yeah in yeah, because some of the part of the particle, not everything will be emitted, some of them will be absorbed by the black hole. So not everything. So this is not because then in the high energy limit
So not everything escapes.
not everything is in the high energy limit. I mean the energy of the particle is much bigger than the I can say then this goes to the so-called geometrical optic reading.
So which is RG squares.
Yeah, I think they have around right. But these are the optic reading. But then at the energy of the particle is lower, so it won't I won't be released for sections. But then there's another just mention although it's not I won't mention. I won't if you imagine all the bosons, so this -1, it's possible that the energy is smaller than angular momentum. So you see that this whole term is negative. But then actually in that case, this absorption cross section becomes negative. That means it actually the incident is much smaller than the reflected. So it's still positive. There's a so-called superradiance condition. So when your spin and the angular momentum, the Z axis, when Q is much bigger than omega, bigger than omega, then have a superradiation. When this actually is negative. Then in that case, actually you get exponential, you get spin loss by fast the difference in speed. They extract all the spin. It only happen for bosons.
So what happens when the energy equals m omega?
Energy, I'll say there's a beginning of
Superradiance.
Yeah, because when this okay, then 1 minus 1.
Yeah. So that's superradiance. That's what's called.
Superradiance is usually this is smaller than this, so this term becomes negative. Yeah. But then I don't know exactly equal. Yeah,
The integral is probably okay.
yeah. I don't know, yeah, I have. I'm very slow. Okay, okay, just to mention about what we expect for the mass of the black holes. So again, there are various ways to form. So one is you have a large density fluctuation. When this large density fluctuation get into the horizon, so then you can start to collapse and form the black holes. So then you can estimate the mass of the black hole by the size of horizon at that time. So for example, if you assume radiation dominated universe, this assumption. After inflation. And then this Hubble rate is a simple expression. Fast. And we have the radiation density. And then you can estimate the direction by the thing, black hole rest that is one function. For example, our volume. Multiply by the okay. So from that, multiply by the energy density. Initially, that a factor the amount that people use to describe this depends on the degree of the collapse. So the estimation that it's a number here. It's not that it's one. Like organization collapse. And then so at the radiation dominator, so the formation time, you know that the time scale at Paulo and one of those two. And then the Paulo radius, different domination, the period is speaking of twice. TF is a function. So if you put this into this equation, and then when black hole will form, what kind of mass will black hole will form at what? So this is the multi. And okay, here basically I use this relation with 1/2 p. The energy density is 1/2 p. So just write down. They become linear in time. So the lighter black hole form earlier, so like you get that the. So this exact film radiation dominator is plus. So again, I just try to put some number. Idea. So we will look and the formation time. Like for example, right before BBM and down BBM, when the minimal field radiation comes. So when they form around this time, so actually this is the field, there are four orders, the solar micros, the right four solar masses. So that means you can form actually black hole vision of the order solar masses. But in general, they form earlier, but they much later. But there's a constraint, how light black hole it can form, what's the lightest possible. They actually come from the Planck constraint of the inflationary upper scale inflation. I think the Planck is I think this five. For the non-normalization of the decimal, the stable ratio limit. So if you put this into here or here, occasion. So that's this you can sort of rewrite as so we can obtain a limit of how what is the lightness black hole, the model black hole. From about 0.1 gram. Then this is convert the temperature for the wave table to convert to the maximum radiation. About like all max because I just use this value. So that means that the lightest black hole you can form is about 0.1 square of the lighter than that. But then you can form up to the order of for these primordial black holes.
Sorry for it, I think that upper limit, it doesn't count for CMB constraints in the, because here I'm assuming that you're including this from the monochromatic.
Yeah,
in the power spectrum, right?
yeah.
So then you will have constraints in the smaller scales of the CMB that I don't know, it will be like, I imagine that will be a little bit less than around 766.
No, you are in this.
No, the upper limit, that's how they can be, they not just spoil CMB.
Yeah, actually, yeah, this is not very up or down. Because I just say that if you are still radiation dominated, because
Yes, like
That's
the
right.
beginning of the region.
yeah, so because we can have universally radiation dominated up till BDN, that's the key. You know, if that will form, yeah, but if it forms during BDN,
You will spoil the
Yeah.
CMB.
yeah. So I'm just saying this is the place that, yeah, we want them to stop before.
Yeah,
It's not really
I get it.
But you don't have a mass function, just say black holes form all with this mass.
Yeah, these are the very simpler assumption, simplest assumption. Yeah. It could just all of them form within mass within the environment. It's a simplest assumption. But in general, yeah, but the in that way, let's see. Then next I will just okay, describe how they this black hole evolve. So there are two main equations. The mass evolve in time. So we should have minus that. I got to multiply. Wait. So okay, then you integrate all possible energy. And then all the possible particles you can emit. So this is how the mass will be used. And then the other one is just how the angular momentum. So yeah, the oil. Yeah, I think I changed the notation. Yeah, it's very long. Yeah, it has. So this will be that's the similar like that of energy. We multiply by the momentum along the axis. This end. Okay, so basically these are the two main equations that describe what that look, how they evolve. Starting from some speed, please starting from first, we reduce. Okay, just one comment about this formula. In general, the duration breaks down. When there's this formula is not then after that we shall be breaks down when the energy of the emitted particle is greater than the temperature of that. So this if you use the formula of the temperature. So basically energy of the rather is the fruit plate of the I try to say is thing of this, rather saying the energy of the particle. This in general is about temperature of the black hole. This is much bigger than the mass of the black hole. See the formula breaks down. So that's why people usually talk about time scale random. Maybe when evaporate until the mass is small enough, so getting reach a time scale. But if you estimate this is MBH, and this is the sound when you are yeah, that's all five. So you get that this is then saying that when the mass of the black hole is smaller than the black hole. So then since you cannot extract this formula, so nobody knows what happened. But one idea is that if you just stop evaporating, then you're left with some plane scale object, which can be a dark matter by itself. If they are stable. It's just an idea, but
So you mean you cannot do this integral to infinity?
right, yeah, in principle, okay,
You have to
this
cut out.
is not, yeah. Well, yeah, when you reach some, no, you can keep evolving until when you reach the length scale, you get stop. So this has to do with later when I show how we estimate the particle production, basically integrate from black hole initial black hole mass to 0, or you stop at some point. But the difference is negligible, so it doesn't really change the amount of particle production. But I think it's relevant if you want to estimate the playing scale random, how much you get. So basically, you'll be just the density of the black hole that you get actually, so that would be that. I think that's then we will talk about possible value. So one thing is is- okay, okay, we can rewrite this formula in certain way, but maybe I just since notation I use, we can define dimensionless parameter. So basically from here we can also change this expression to evolution of the dimensionless state parameter. So we can do this function. And then there's one very convenient parameter that we can. Yeah, we can define this for scale invariant time parameter. So we just multiply by the initial black hole. Then if we define this, we can derive our whole initial that is very and then it all will be there. So you can see roughly what upon V is basically the ratio of the black hole mass to the initial black hole. The ratio. And this F is basically the mass loss function. Which yeah, it's called H factor rather than H to one with the after we define the right now. Then G has to do with this spin off. So basically this function is kind of nice. because they depend, but they depends on the baseline, yeah. And it depends also on the mass of the. It also depends on the mass of the black hole itself. So that, yeah, it will depend. But then the dependence on the mass of each particle. So if the temperature of the black hole initial temperature is much higher than the mass, so basically this function will be completely independent of the black hole mass. Yeah, maybe it's not clear because it's not everything. But then the important thing is if you, for example, if you assume this graph of the black hole, that it can emit all the standard model particles, so essentially you can you can assume that all the standard model particles are zero. If you assume are zero, so these two functions because they will be completely independent of the black hole. They will be parameter of the only of the speed. Right? So the example of the solution that I draw here is just to show basically these two solutions. So this is a ratio of the black hole mass to the initial mass. So this is the spin to the initial spin, so it's 1. But then the initial spin and the 0.1. So you can see that for this is the spin down, so the speed, the ratio, the initial spin reduced. So they essentially go to 0 even before the black hole of the spin down. And the slight difference, I think we can see that one the triangle and the blue line. So the lifetime is a bit longer if you don't include graviton. But if you include graviton, it's just like 2 degrees of freedom. So basically the lifetime is a bit shorter. Also the spin rise a bit faster when you include graviton, but graviton accelerates higher speed. And then this effect is more obvious if you consider the speed of the black hole is greater. So it is without and then you can also notice that the lifetime is actually considerably shorter by about factor of half. That means if you put spin or not, the lifetime of the black hole can change by say up to a factor of 2. This is so then the lifetime. So yes, now a bit about the lifetime of the black hole.
So this is without baryon method. This is not standard model.
Yeah, this is only standard model without
Really
graviton.
without.
Because if you put dark matter, actually it depends on the speed. So it just an additional 1 degree of freedom. But if you put a heavy mass, then essentially doesn't change because the heavy mass, I mean, it's still dominated by the particle with mass smaller than the initial. But you see how much. So this will change by a bit because it's 1 or 2 more degrees. Very dominated by standard. So actually can solve the black hole lifetime came from the top written as E in the rate. So since we integrate with DZ that means we start from 0. So it's the law of the ratio. So 2 negative infinity. In fact, you can stop, but you don't have to stop at. You can start at down scale and the mass, but essentially, yeah, the lifetime doesn't really change. So for the standard model particles, if the black hole is yeah, basically you can solve it analytically in speed. So we can solve this assuming all the particles are the mass is much smaller than the initial temperature of the black hole. Okay, there are many assume. Also, you assume that because this cross section actually depends on the energy of of the emitted particle. Okay, yeah, this is absorption cross section. This from the black hole, you know that's the code, black hole. So they actually have this absorption cross section compared to the geometrical activity, it's a ratio. So you can see that at a high energy, so basically they oscillate around the geometrical cross section, but then they are very different at low energy. So if you use this gray body factor in general, you get a black hole with a longer lifetime because this cross section is smaller. They get slightly longer. And, okay. Okay, I will write down the lifetime right now. So this, the lifetime, if you assume geometrical optic limit, this is the lifetime. And we can do this integration. Yeah. So okay, this is stop. So now if you want to convert to physical type, you just multiply by the initial black hole mass with the key. So this is invariant. The black hole mass can convert to the physical lifetime. Multiply by initial black. Then if you put in some value, yeah. You can the ideal value to get to it. Is the end. So we see that the black hole with the mass of 10 to the 9 grams, so they'll black hole rate now close to the BBM. So because there's a very strong constant to show the plot. So basically, if you want to consider a primordial black hole, that you're going to use for dark matter production of baryogenesis, which happens before BBM, then their mass cannot be greater than 10 to the 9. It has to be lighter than 10. So that they evaporate before BBM for baryogenesis or to avoid the strong constraint for BBM. Yeah, because for baryogenesis, it doesn't make sense to talk about, happens after BBM. So what we are interested in is black holes lighter than 10 to the 9, and then then has behavior that from one gram. This is the range that we are interested in.
Just so the is that they all operate before BBN.
Yeah. Because then I'll show the plot later. If you do the estimation of the lifetime of the universe, then if you want them to black holes, it will be the dark matter, then this will be about 10 to the 15. So then you get 10 to the 17 centimeters. So for to be a dark matter, then there will be heavier than 10 to the 15.
But they're not considering this case.
So we are not considering black hole itself as a dark matter, but the dark matter produces the black hole.
And what's the typical mass of the PBH to generate the supermassive black hole? Should we see it of the supermassive black hole?
Seed is supermassive black hole. But seed of the supermassive black hole should be much sure than mass.
But I don't think it is known how supermassive black holes form. I mean, it's not fully known. I mean,
Yeah, it is one possibility, right?
the seed comes from.
It's the supermassive black hole.
Yeah, but then you need to know how much mass is accreted by gas, how much mass is accreted by successive mergers.
Yes,
So
that's the question.
very unknown.
Okay.
So can you repeat again? So you will form this primordial black hole before BBN and then will go post.
Yeah,
Because you will not see it now.
Yeah.
You will not affect.
anything right now.
Yeah, so they have to be lighter such that they are correct for the gravity. Then what constraint, but I will also show that if you include even an almost maximally spinning black hole, okay, this is a geometrical optic limit. So if you include the full gray body sectors that top, so you get something which changes by not much. You get so this is the full gray body sector. You get this modified, then you get it goes slightly longer life. The first section you see that it's not slightly smaller, lower energy. Then if you include the maximally speeding, then a very large a speed of that you have. Then you get it to be shorter. Yeah, that's to say that the type of speed of we wanted that doesn't change by a lot from this investigation. So the answer of that both is all days of good and good. Because of yeah, well, then comment if you want the background to be order of the age, then the mass. Okay, there's still space, even though even if you consider monochromatic, there's still space for the black hole to be fully dark matter. But it's not the yeah, but I think yeah, I just write down the calculation of the formula that basically for the production.
When black holes produce dark matter.
Yeah.
Operation.
Okay.
So in order to compute dark matter abundance, you have to know how many black holes are there.
Right.
And then you have a theory for it. How many black holes are there?
No, not really.
So how can you compute?
No, just it's a free parameter, right? You just work in this parameter space. And then show what are the possible constraints that's already there. Then in that parameter space, where you can still get
Well, I think you can estimate the number density just with the speed to the power spectrum and like the speed. We got
And
these
then you need a
numbers.
model for power spectrum, we should know that.
Ah, yeah. Yeah, right, assuming that it's talking about monochromatic, then it implies that you have a power spectrum localized. Otherwise, we have another mass profile, I think. Yeah,
Is it different from parameterizing like equal?
not really.
And then we have about the branch then, which is the beta that is the final formation. By the so this there's a number that is still multiplied by the amount. But then if you are interested if the black hole in the particle produced from the black holes, okay, so that you write out for from one black hole, you can calculate how much for this. So for one, so the number of particles that are infected, if which is produced, you have the have this emission probability rate. So this is just the integrate over all the energy. Then after that, you have to integrate over the lifetime. Starting from 0 time until the lifetime of the cycle. So this is just the way we calculate for one black holes. So now if you have a bunch of them, yeah, maybe I'll just show the result. You can get some approximate results just to understand the behavior. Here. So one is in the mass of the particle that you would like to produce. That's it's much lighter than the initial black hole mass. Initial black hole. The other one is when so you can see that in these two units, in one unit actually you'll be completely independent of the mass of the particle that you are producing the result. But in the other unit, you'll be suppressed as you increase the mass. So this is the result. One is that the black hole mass square with some numerical factor which write it down. But then in the other limit, when the particle that is like to produce steady, so you get a suppression, right? The mass of the particles. Yes. Okay, naively, we usually think about exponential suppression, but this doesn't turn out to be exponential. It just because as the black hole gets smaller, it gets hotter. So that actually the behavior turns out to be 1 over the mass. Okay, so this is you can see this is how roughly we estimate how much particle can produce. Okay. So now, if we have this bunch of initial black holes, so we can just now we can just multiply. Yeah. Okay, this is the number of particles, number density of particles per entropy density that we expect to produce. So this is when during the evaporation, and then assuming that from the beginning to the evaporation time, the entropy is good, so we write things as the initial number density of the black holes. So this will be the entropy at the time. And then this the x you can rewrite in terms of radiation density. So entropy density is basically is related by is a 4/3 temperature. So you can rewrite this in terms of data. Data. Temperature. Multiplied. So this is the number of particles for each black hole. So now you can go to how much you. This will be the number of particles. But of course, it's possible that if you have too much black hole, it dominates the energy density of the universe. So you get entropy directions. There are two regimes. The one regime is because it depends on the lifetime of the black hole. So if the black hole is too long-lived, since it behaves like matter, then it can overtake the radiation density. Because matter drops slower than radiation. So in that regime, you can take into account what we have to take into account. So, so one, this is a rough way, turns out to be quite good. So it estimates, energy density of the radiation at evaporation of the temperature. Okay, this is radiation plus the black hole radiation. And zero, time. The evaporation time. So we are looking at the evaporation time. This is bigger. But then they have to equal, assuming all of them evaporate at this time, so it becomes the rotation. It's the radiation temperature after. So basically the entropy dilution is just proportional to the temperature after. Divided by one plus the dilution divided by T. Yes, we usually in particle before sudden decay approximation, sudden leveling is the approximation at this time. Then when you reach the lifetime, so all of them become application. We can say this direction. So for certain beta value and depend on the evaporation, so if this is bigger than 1, then the entropy direction is important. Otherwise, it's essentially this value. So the actual value alpha is 0. And the actual value is just is 0. Divided by this possible dilution. Maybe is divide by this is over. So this is the evaporation, something we can estimate, just saying that the lifetime is equal to the Hubble rate. So, so this data that we introduced, that there's a constraint. So this is basically the constraint coming from assuming the black hole is lighter than 10 to the 9 grams, so they evaporate before the end. So, but then these constraints derive assuming the black hole dominates. That means this term is much greater than 1. So in that case, you have a transition from matter domination universe to radiation domination. So during this period, yeah, according to the paper, you have this oscillation in the curvature fluctuation that produces variation. And this amount of radiation is like radiation, additional radiation. So it affects the expansion of the universe. So it affects yeah, so you cannot have too many dark radiation. This gravitational wave by the dark radiation. So from this constraint, they obtain a constraint of the beta, define that. But this constraint involves from black hole mass lighter than 10. The reference value they put in. So maybe the plot I will just draw all this. Okay, so this is one of the plots which they show the constraint for a whole wide range, the black hole mass. So what we are going to see this dash line is basically beyond this is a dark matter, but they are stable. So here they are not stable. Then around 10 to the 9 grams, their lifetime beyond this, their lifetime is at a strong constraint because they will evaporate during PDM. So the long reactions. So they have to be super slow. Okay, this beta prime is just the absorb this gamma. Let me say it's actually the different effects. I don't know order of the factor of 10 major gravity. They define this by absorbing gamma side. Is also the statistic because there's a point value is about, I think it's like 1. So basically they use this data point. And so you can see that below this, okay, this is what I mentioned. So we are not here actually get the 1 gram. But from here to get to the nice area that you can work with for bioluminescence or dark determinant. And then this is Planck, I think the Planck reference box. We have if a black hole actually evaporate in that hole of time. It's not. This depends on the model, but if it is a supersymmetric model, then the black hole generates too much. And then you also have this entropy. This I believe, I'm not sure. I believe it's the same down as here. That broke down. And this is just another plot. Okay, this is actually another plot that not quite relevant for what I will talk about. This for if the black hole can be the dark matter, they are not above here. So basically, it's a range of the famous range that you can have 100%. So this fraction is just a fraction of f. It's a fraction of black hole. The fraction of that. The one remain 100% gravity. And in open range, even if one remain, still accommodate. Okay. So I think I'll just move on. Now we'll go to the evening. 10 minutes. What minutes in it? 10 minutes. 10 minutes to do. Okay.
Yeah, super late.
But then, right, okay. Yeah, I just presentation. So yeah, just write down the main idea that I get from the space. I think I can do it in a few minutes. So right now the observe number of capital mobilize the entropy. The baryon. So respectively. And then we like okay. Next, these two numbers, trying to look at the separation. So, that method. Yeah, the first one that I mentioned is that some skill and data. Then here if we write it down, we just that the skill and but if you want it to be a particle emitted from the black hole itself, then this formula basically just multiply by this that but it's a big multiply by I suppose it will be how much nothing that itself. And then for bio 3. So again, this generally depends during model better, but we would like to see what is the maximum possible particle space. So let's say this is a model particle. So then they get became some intermediate particle that depending on the models. What these are, here's the branching ratio. Then during this eventual this particle produced, so that support efficiency factor. So it's one is completely efficient, completely out in the view. Then that's the factor which are drive for equalization. It's the efficiency. Then the CP meter. Microparticle physics. It has to be smaller than what you got the loop correction. I like that. When you have to look at the parameters, then you actually I think very a very simple method, like just to see what you get. The most maximum 70 or the model that is being on to be inside the and just show you the so basically this is the result for the thing for the biogenesis. So this is a mass of the parent okay. So the parameter space and variable will be inside. So on this boundary, meaning that you set everything to 1. So when this is smaller, so you have to keep inside. So then if you take this smaller particle to be lighter, so get a larger parameter space, the data level mass. And then when this smaller particle has mass below 10 to the 5, actually 8 conversions. So remember the solution I show you. When it's light enough, it's independent of the particle mass. That is the result. When it's light enough, so the number of particles produced doesn't depend on the mass of the particle produced, because the particle mass much smaller than the temperature of the tank. So basically, this is so everything for all the particles, the mother particle can be as large as 1 GeV. All for this one. So basically, for let's say for 10 to the 5 or 1 GeV, it's the same parameter space. For the so that means this is all the possible parameter space that can really get for biogenesis. Even you can assume that your biogenesis happens very late, but after electronic phase transition. Yeah, but before BBM, this is all the parameters space that they get. And then this is about from this data. Yeah. So the last block from this last block. Yeah, last actually there are heavy and last block. So this is if the dark matter is heavy, motor heavy volume, okay, that's fraction. But then this is what the biogenesis parameter space that put on it. But then this is the mass of the dark matter, 10 to the 19. And then I don't go beyond that, 17 GeV, 15 GeV. So it has some common parameter space up to about 10 to the 11. And then this control line is, if I assume, I give this result, if I assume blank still diagonal, so then this will be where you can explain the dark matter for time scale. And then the last one is just the light dark matter, which is very light. Because there are two solutions too. When it's very heavy, it suppresses number density, that's why it's super heavy. But when it's light, it has a huge number density, that's why the mass is big. There are two solutions. So these are the solutions for the light. Okay, just the final comment is that in fact in this area, most of we haven't included, but most of them are not viable, because they will do lot. They will reduce very realistically. The actually structure formation will have this problem. Okay, that's it. Are we getting the other time? I don't know how much.
Okay, I came late, so I might have missed the bottom line, but so you want your primordial black hole to evaporate, but before they evaporate, they are dark matter or not? I mean, they are a good fraction of the energy
Yeah,
density. No, they are subdominant.
they have to evaporate before the BBM, so they have to have short wave time.
Yeah, but
That's
before,
1 second.
before they evaporate, they are subdominant.
Okay, this is this beta. So this is the fraction of the dark matter energy density with respect to the radiation energy density. So they have to be like -4, they have to be.
I will that work.
This is at the epoch before the BBM.
No, but I mean, change the redshift, the refraction now, because, I mean, or are
No,
they?
this is initial, sorry, this is the initial formation time. Where's the beta?
Yeah, but then they become non-relativistic at some point, so they will overtake radiation.
Yeah, basically, if you see the curve where they change the plot, so this is the area where they become the dominant energy density of the radiation.
Yeah, but then if they become dominating or a significant fraction, and then they evaporate into radiation, there's a problem with BBA, because we cannot have extra.
Yeah, but this happened before the BBM.
No, but I mean, we cannot have extra equivalent species of neutrinos.
Yeah, but they evaporate the radiation, so it's not additional, it's just the second one, it's just the photons eventually. Because they don't evaporate to the additional radiation, additional species, I mean. Okay, assuming there's a standard model, so they dominate the energy density, then after that, they evaporate completely, still to the second model radiation. So
Okay.
what happens is that you get entropy.
Okay, but then what do they must evaporate in gravitational waves too, and that's heavily bounded.
Yeah, this is the bound for the radiation domain, which is additional radiation.
On here,
This is additional radiation.
so that comes from the equivalent number of neutrinos. That
And then we for the BBN.
Okay, sorry.
So this is the area. It's not have
Yes, well,
So are you planning maybe to explore different transport profiles instead of monochromatic transport?
yeah, there's a possibility to figure that.
Because then they would have that everything changed with Dredge, so.
Yeah.
that's
Yeah,
that one big-
but yeah, I'm not sure we will jump into that because the next stage they will take of training super radiance. When doing the speed, so but they haven't gone in this direction, but this is one of the big things.
yes.
Yeah, I think that related with other questions. You have constraints to beta and the mass of the primordial black holes. Can you translate to some constraints in the action of the inflow, for example?
Yeah, because all this will still happens after inflation, even the formation.
Right, but you need to have something in the power spectrum that explode that generates by the power spectrum.
We need a fluctuation.
Yeah, so maybe you can, I don't know, fix the mass scale of the inflaton or the auto interaction of the inflaton because of the height of your peak, the power spectrum, I don't know, the primordial of power spectrum.
Yeah. Yeah, we haven't really talked about that, yeah, about the formation between the.
So I have a question. So there's this factor of 5 between the dark matter abundance and the baryon.
Yes.
In your model, is there a way to explain this factor of 5?
I don't think so, I don't think so. Yeah, because for example, in this common parameter space for this. Okay, like we say, you can see that the mass of the parent particle will be very heavy. And then when they converge to this line is all the masses which have smaller than 10 to the 5. But then on the other hand, if you look at the mass of the dark matter cloud, you can have heavy solution, which is quite heavy, or light solution, which is very light. So it's still, I would say, it's a coincidence.
So if there are no further questions, let's thank Sheng again. Okay, discussion, thanks for discussion. There's some, but before we.
Yeah.
You're.
No. I was just.
Yeah, yeah.
because we are still organizing this thing, and the idea is that it has as many points of view possible. I mean, this was kind of just a few people talking, but I mean, just by looking at what are here, we see lots of people that are working in anything from, deep down galaxies to building galaxy service, to exploring that galaxy service, to gravitational waves and everything else. The idea is to have everybody represented here. Otherwise, this doesn't become interesting to everybody. And then we just essentially, this doesn't work. So the idea is to have next time more different points of view, different areas of research. I think we missed today things which are deeper into galaxy service, which is many people here do this.
I think
maybe next time. Yeah, we definitely need that. I also suggest that we have shorter talks, because otherwise we don't have time to discuss. I mean,
Yeah.
this
This is the first one, we're just
Yeah.
trying out. Okay, so
Yeah.
if you have any feedback, like I was saying, let us know. Also, please, if you didn't put your names in here, just put your names, because yeah.
we need more food next
We need
time.
more food next time. We're paying for our success.
Yeah.
So,
So maybe we can already start thinking about
Yeah.
next time,
Yeah, yeah.
perhaps, right? I mean,